Ever get that feeling where AI seems so smart it's almost creepy?
Hmm.
Like it just aced a math problem that would make your head spin.
Yeah.
Well, today's deep dive might make you think twice about those AI geniuses. We're taking a hard look at large language models. Those are the brains behind a lot of the AI you see out there, and their not so stellar track record with math.
Yeah. It's tempting to think their math whiz is right.
Right.
But we're going beyond just checking if they get the answer right.
Yeah.
Today, we're looking at how they actually arrive at those answers.
Exactly. We're cracking open this research paper called GSM-Symbolic, Understanding the Limitations of Mathematical Reasoning in Large Language Models.
Oh, okay.
And, spoiler alert, it gets a little awkward for those LLMs.
Yeah, the researchers really wanted to understand if these models were demonstrating true mathematical reasoning or if something else entirely was going on.
So let's break down how they did that. They started with this thing called the GSM-8K benchmark, essentially 8,000 grade school math problems that act like a standardized test for AI. Sounds like a solid starting point, but there are a few catches, right?
Right. One concern was data contamination. These LLMs are trained on mountains of data, and there's a chance some of the test problems might have snuck into their training.
Mm-hmm.
That would mean they're not really solving the problem, just remembering the answer.
Kind of like acing a test because you accidentally got a sneak peek at the answers beforehand.
Yeah.
So how do you make sure the AI isn't cheating off the cosmic crib sheet?
Well, the researchers created something pretty ingenious called GSM-Symbolic. Imagine taking a math problem and changing all the details, names, the objects, the numbers, but keeping the underlying math the same.
So same problem, different outfit. That way the LLM can't just rely on memorization.
Precisely. They tested 25 different LLMs, even those big names you've probably heard of like GPT-4,
Right.
and had them tackle these GSM-symbolic problems.
Okay.
And here's where things get interesting, if not a little concerning.
Let me guess, the LLMs didn't quite get straight A's.
Not consistently. They found that all the LLMs had wild swings in performance, depending on how the problem was phrased. Remember, the math itself was identical, just dressed up differently.
Hold on, so just changing a few words or numbers threw them off that much?
It did, and that's not how you'd expect a human who understands math to behave.
Right.
The paper even gives this stark example. An LLM might score 90% accuracy on one version of the problem, but tweak the numbers slightly and it bombs, scoring maybe 20%.
Yeah.
That inconsistency was a big red flag.
That's a serious reality check for anyone who thought these LLMs were math geniuses. What does this mean for the average person using these AI tools?
It highlights a crucial point. Just because an LLM spits out the correct answer doesn't mean it understands the math behind it. And that distinction is crucial, especially if you're using these tools in fields where accuracy is paramount.
Absolutely. I'm thinking about things like finance, engineering, medicine areas where a wrong answer could have serious consequences.
Yeah.
So if they're not really understanding the math, what is going on in those AI brains? Are they just really good at guessing?
It's more nuanced than just random guessing. It seems they might be relying heavily on pattern recognition. Think about it, they're trained on this massive amount of text and code. Within that data, there are patterns.
So they're basically picking up on those patterns and applying them superficially without truly grasping the underlying concepts.
Exactly. They might be able to spot the equation that usually fits a certain type of word problem,
Right.
but they don't necessarily understand why it fits.
Okay, so they're like those people who memorize dance moves without learning the rhythm or the music.
That's a great way to put it. And because their understanding is so surface level, it makes them vulnerable to these inconsistencies. Change the wording even slightly, disrupt that memorized pattern, and their performance can completely tank.
So we've got these LLMs, even the ones with fancy names like GPT-4, tripping up on what seems like pretty basic math. But the researchers didn't stop there, did they? They dug even deeper into this whole fragile reasoning thing. What else did they discover?
They wanted to see what kinds of changes were most likely to trip up these LLMs. So they ran experiments where they either changed the names in the problems, like people's names or places,
Okay.
or they changed just the numbers again without altering the actual math.
So they were testing if it mattered if it was apples being added or oranges, as long as the addition part was correct.
That's a great way to think about it. And the results were pretty telling. Changing the names in the problems did cause some variation in performance, but changing the numbers, that really messed with them.
You're kidding. So they were more thrown off by a 5 becoming a 10 than Sarah becoming Michael. That's kind of hilarious, but also a little mind-boggling. What does that tell us about how these LLMs are approaching these problems?
It circles back to that idea of pattern matching. They seem to be latching on to the numerical patterns in their training data more strongly than the semantic patterns.
Okay.
When you change the numbers, you're disrupting those numerical relationships more significantly, and that leads to those bigger drops in performance.
Okay, so they're not just memorizing the entire problem, they're picking up on these deeper numerical patterns, but then they get completely derailed when those patterns change even a little. It's almost like they're missing that flexible, adaptable way of thinking that humans have.
Exactly. They're not transferring their knowledge in the same way humans do.
Right.
We can usually apply what we know to slightly different situations.
Right.
But LLMs seem stuck in these rigid patterns.
So it's not just about having a massive database of information, it's about being able to work with that information in a truly intelligent way.
Right, and it becomes even more apparent when the researchers started to tinker with the complexity of the math problems themselves.
Okay, so how do you make a grade school math problem more challenging? Did they bring out the algebra?
No need for algebra. They kept the math simple, but they found a clever way to ramp up the difficulty. They started adding or removing clauses from the problems.
Okay.
Think of a clause like an extra step or piece of information in the problem.
Okay, so instead of just saying there are 5 apples, they'd add something like, and 2 of them are green.
Exactly. And what they found is that as they added more clauses, essentially making the problems longer and more winding, the LLM's accuracy dropped. But it wasn't just that their overall scores went down, the variation in their scores also increased.
So the more steps there were in the problem, the less predictable the LLM's performance became. That almost seems worse than consistently getting the hard ones wrong.
It really highlights the fragility of their reasoning process.
Yeah.
They can handle a few steps, especially if those steps fit a familiar pattern, but as the problems get longer, more convoluted, they seem to lose their grip on the logic.
It's like they can follow a simple recipe, but ask them to make a multi-tiered cake, and it's a recipe for disaster.
A very apt analogy. And this is all before the researchers unleashed their final test, which really exposed the limitations of these LLMs.
Oh, there's more. Give me the grand finale. What did the researchers do to really push these LLMs to their limits?
They designed a test called GSM-NoOp. Imagine you have your math problem, and then they slip in a piece of information that sounds relevant, but it's completely useless for actually solving the problem.
It's like hiding a secret message in a fortune cookie, except the message has nothing to do with the fortune. Give me an example.
Okay, let's say the problem is about how many kiwis Oliver picks.
Okay.
He picks 44 on Friday, 58 on Saturday. Then on Sunday, he picks double the amount he picked on Friday. But 5 of the kiwis were smaller than average. How many kiwis does Oliver have in total?
Okay, so that last bit about the smaller kiwis, that's the irrelevant information.
Exactly. A human would read that and immediately know it doesn't affect the total number of kiwis.
Right.
But the LLMs, many of them fell for it hard.
Wait, they actually tried to factor in the size of the kiwis?
You got it. They were thrown by that irrelevant detail, and the results were pretty dramatic. Across the board, the researchers saw huge performance drops on the GSM-NoOp problems, sometimes over 65%, compared to the same problems without the misleading information.
So even a tiny distraction, something that seems so obviously irrelevant to us, can totally derail their process. That's both fascinating and a little alarming. I mean, these are supposed to be these advanced AIs, but they're getting tripped up by misleading Kiwi facts.
It really underscores the fact that they're not thinking like humans. They don't have that innate understanding of context and relevance. They're desperately clinging to patterns, and when you throw a wrench in those patterns, even a wrench that seems nonsensical to us, it can totally throw them off.
Okay, this is really making me rethink what it means for an AI to be intelligent. So given all of this, what happens when you try to correct these LLMs? Can they learn from their mistakes? So it's like they got an A+ on the vocabulary quiz, but completely blanked on how to write the actual essay.
That's a great analogy. They've memorized the words, but they haven't grasped the deeper meaning or how to apply them flexibly.
Okay, so we've established that these LLMs have some quirks, to put it mildly, but there's got to be a way to fix this, right? Can't we teach them to ignore the irrelevant stuff and focus on the actual math?
The researchers did try a few things. They showed the LLMs more examples from the GSM-Symbolic set,
Okay.
hoping that seeing the same problem in different outfits might help them catch on. They even tried fine-tuning some models on tougher problems, essentially giving them extra practice.
So did any of that work?
Sadly, not really. While there were some small improvements, the irrelevant information continued to trip them up. Even with the extra training, they struggled to consistently identify and ignore those misleading details.
You'd think with all that data and processing power, they'd catch on eventually. It's almost like they're stuck in a loop repeating the same mistakes even when they're shown the right way to do it.
It really highlights a fundamental challenge in AI development.
Mm-hmm.
We can build these incredibly complex systems, but teaching them to think critically and adapt to new situations, that's proving to be much trickier.
This is where it gets a little philosophical, right? We're talking about the difference between true understanding and just mimicking intelligence.
Absolutely. And for those of us who use these AI tools, it's a crucial difference to be aware of. We can't blindly trust these models to reason their way through complex problems, especially in fields where the stakes are high.
So where do we go from here? What does this mean for the future of AI? Are we destined to be ruled by machines that can write amazing poetry but can't tell if a kiwi is relevant to a math problem?
I wouldn't say we need to panic just yet. This research is incredibly valuable because it's revealing these limitations and pointing us in the right direction instead of just focusing on getting LLMs to score higher on benchmarks. We need to fundamentally rethink how we teach them to reason.
So it's back to the drawing board for the AI architects out there.
In a way, yes, it's about finding ways to instill these models with a deeper, more flexible understanding of the world, not just a superficial grasp of patterns. We need them to think more like mathematicians, breaking down problems, logically identifying truly relevant information, and adapting their approach as needed.
It's like, instead of just giving them a faster calculator, we need to teach them what those numbers actually represent and how to apply mathematical principles in different contexts.
Exactly. It's a much bigger challenge.
Yeah.
But ultimately, that's what's going to lead to truly intelligent AI systems that can not just process information, but understand it in a way that's closer to how humans think.
Well, I, for one, am both excited and a little terrified to see where this all leads. But hey, that's the future for you, right? The big, beautiful, slightly unnerving mystery waiting to be solved. For our listeners who want to explore this research further, and trust me, it's worth a read, we'll link to the full paper in our show notes. And who knows, maybe one of you will be the one to crack the code of true AI reasoning. Until next time, keep asking those deep questions, and we'll be here to dive into the answers.
Hey everyone, welcome back. Ready for another deep dive? Today we're tackling something that's got me seriously wondering. It's AI, but specifically, how much do these systems really get math?
Ooh, that's a good one.
Right, like we're blown away by what large language models can do. Writing code, emails, you name it.
It's easy to think, well, they've got math figured out then, right?
Exactly.
Yeah.
But is that true? What about just basic arithmetic? Is that their weak spot?
You're hitting on a huge point. See, there's all this hype about AI reaching human-level smarts, but math, reasoning with numbers, logic, that's a whole other ballgame, it turns out.
Okay, so get this. I was reading about this GSM-8K thing.
Yeah.
Basically, they give these LLMs a test, bunch of grade school math problems.
I've seen those.
And some of the scores have been really impressive, haven't they?
They have.
Yeah.
There's this new paper out, GSM-Symbolic, and, well, makes you wonder if those scores are telling the whole story.
Ooh, juicy. What'd they do?
So they took those same GSM-8K problems, right? But they created tons of variations.
Variations how? Like, say you've got a word problem about Sophie. They might change it to Oliver. Or if it's about toys, they'll tweak how many toys there are. Little things.
Okay. But why does that matter?
Because think about it. If an LLM really understands the math, those changes shouldn't matter much at all. Just like you or me, right?
Sure. We wouldn't care if it was apples or oranges, so we'd still get the addition right.
Exactly. So this is testing if it's real understanding or if the LLM is just pattern matching. Seeing a similar problem and spitting out an answer without truly getting it.
So what'd they find? Spill the tea.
All right, so get this. Even small changes, like really small, made the LLM's performance go all over the place.
No way. How much are we talking?
Accuracy dropped by over 10% sometimes. Just from, like, swapping a name or changing a number a bit.
Wait, seriously, so just changing Sophie to Oliver messed them up. That's not great.
Not great at all. And that's what's setting off alarm bells, right? This inconsistency. It hints that maybe these LLMs are leaning hard on those surface-level patterns instead of understanding the math underneath it all.
Yeah. So maybe they're not winning any math awards anytime soon, huh? But, like, the real world's messy. Does it matter if they're not perfect mathematicians as long as they mostly get it right?
That's what you'd think, right? But it gets even wilder. They did this other thing called GSM-NoOp. Basically, they added sentences to the problems. Sentences that seemed important, but they didn't actually change the math you needed to do.
Oh, interesting. Like a little misdirection. Give me an example.
Okay, so say the problem is figuring out how many kiwis there are, right?
Mm.
GSM-NoOp might add a sentence like, some of the kiwis were smaller than others.
Okay. Seems like it could matter, but it doesn't change the total number of kiwis.
Exactly. So it's like
Yeah.
they were trying to distract the LLMs, see if they'd get thrown off by this extra info.
Sneaky.
But-
And did it work?
Oh, it totally did. We're talking huge CE accuracy drops.
Yeah.
Like over 65% on some of these GSM-NoOp problems.
Whoa, seriously, 65%?
Yeah, it's like they got so caught up in the details, they completely forgot what they were actually supposed to be solving.
It's kind of like...
You're reading an article, right?
Yeah.
There's this little side comment that catches your attention, and you totally lose track of the main point.
Perfect analogy. And that's what's kind of scary, right? This research is hinting that these LLMs, as good as they are at sounding smart, they might not be understanding the information the way we do.
Right, right. Even something as basic as math. It's like,
Right.
where we're impressed by the surface, how smoothly they talk, but underneath, maybe not so much.
Exactly. And that's a big deal. We're relying on AI more and more these days, everything from healthcare to, well, you name it. And we need to know what it's good at and what it's not.
Totally. It's a reality check, for sure. We see these headlines, AI is going to take over the world, but maybe the bigger issue right now is we're overestimating what they can actually do.
100%. This research is a good reminder. We got to test these systems carefully. We can't just get swept up in the excitement and assume they're more advanced than they really are. Yeah, it's like thinking a self-driving car can handle any weather just because it drove fine on a sunny day, right? We got to know the limits before we hand over control.
Exactly. And with LLMs, that means digging deeper. It's not enough to just see if they can spit out words that sound good.
Yeah.
We got to see if they actually understand what they're saying.
So where do we go from here? How do we figure out if these LLMs can actually understand, not just mimic really, really well?
Yeah, it's kind of a wake-up call, isn't it? Like we need to maybe adjust our expectations a bit, not hit the brakes on AI, but proceed with a little caution.
I'm with you on that. And it's not about, being scared of AI or anything.
Right,
It's more like, let's be realistic about what it can do right now so we can build it responsibly, ethically, all that.
Totally, totally.
Yeah.
So where do we go from here? If we want to know if these LLMs can really, truly understand, not just mimic, but understand,
Yeah.
how do we figure that out?
That's the question, isn't it? It's what everyone's grappling with. One thing researchers are looking at is trying to make these LLMs more transparent.
Well, right now, they're kind of like black boxes. We feed in data, out pop the answer.
But we don't know what's going on in the middle.
Exactly. We don't see the process. So if we could peek inside,
Right.
like
Yeah.
understand the steps, the logic,
Yeah.
maybe then we could spot what's missing.
Okay, yeah, I get that. Like, I know this recipe makes an amazing cake, but...
But you don't know the why behind it.
Right, the chemistry, the reactions. So with LLMs, it's about figuring out their recipe, so to speak.
It's a good way to put it.
Yeah.
And, the more transparent these systems are, the more trust we can build, too.
Oh, for sure. If I can see how you got to that answer, I'm more likely to believe it, right?
Absolutely. Transparency is huge, both for the researchers, but also for all of us who are going to be using these AI systems more and more.
Makes sense. Well, this has been a fascinating deep dive, I'll say that. Seems like AI, it gives us answers, but it creates even more questions. If our listeners take away one thing from today, what would you want it to be?
One thing. I'd say LLMs, they're incredible tools, seriously powerful, and they have the potential to change, well, pretty much everything. But we can't mistake their fluency, how well they use language, for actual understanding. Just because an AI can write a beautiful poem or code like a pro,
Yeah.
it doesn't mean it gets the concepts behind it.
Well said. Really makes you think. It's all about finding that balance, right? Being excited about AI, but also being a little skeptical, asking tough questions.
Exactly. Can't just believe the hype. Got to stay curious.
Could not agree more. Well, thank you so much for joining us today. It was a pleasure picking your brain.
Anytime. Always happy to chat about this stuff.
And to all our listeners, thank you for joining us on this deep dive. Keep those questions coming. And until next time, happy exploring. Ever get the feeling that AI is kind of like that friend who, pretends they've read the whole book, but really they just skimmed the spark notes? Well, today we're doing a deep dive into some new research that puts those AI math skills to the test, really puts them under the microscope.
Yeah, and we're going beyond just like looking at those surface level accuracy numbers. We're talking about what these models, these AI, actually understand about math. And honestly, the results are, Well, let's just say they might add up to a different conclusion than you expect.
Okay, so let's break this down a bit. Our starting point here is GSM-8K, which is like what everyone uses as the benchmark for testing AI on math, right? It's a whole data set of grade school math problems, the kind you'd see in like a textbook.
Right, like classic word problems if Sarah has 3 apples.
Exactly. And I'm thinking, okay, if an AI can write a sonnet, it can handle figuring out how many cookies are left after a picnic, right? But it's not quite that simple, is it?
Not so fast.
Yeah.
See, this paper we're looking at, they're arguing that GSM-AK, it might not be the perfect measuring stick because it's static. See, it's the same set of questions every single time. And the researchers, they're suggesting this could lead to data contamination, which can really throw things off.
Data contamination. Now, that sounds kind of serious. What exactly does that mean in this context?
Okay, so picture this.
Yeah.
You've got these AI models, right? And they're being trained on oceans of data, like an insane amount of information.
Right.
So there's a chance, and it's a pretty decent chance, that some of those GSM-AK problems, or at least problems super similar to them, they might have already snuck into that training data. And if that happens...
It's like giving them the answers ahead of time.
Exactly. They might be acing the test, but not because they understand the math, just because they've seen those exact questions before.
So it's not about genuine understanding. It's more about recognizing something familiar, like those students who S a test by memorizing the answer key, not by, actually learning the stuff.
100%. And to test this whole idea, the researchers, they created something called GSM-Symbolic, which is a brand new benchmark, but it's built from these customizable templates.
Customizable templates. So like Mad Libs, but for math problems.
You got it. They took the math problems from GSM-8K and they figured out how to swap out the numbers, the names, all those little details, but they kept the actual underlying math structure the same.
Clever. So same type of problem, just with like different characters and numbers. Did that trip up the AIs?
It did. Even those small changes, just tweaking the wording a bit, it caused some of those LLMs to stumble. Their accuracy started varying a lot depending on how the question was asked.
Wow, so even just the way you phrase it matters? That's wild. What does that tell us about how these LLMs are approaching these problems?
It really seems like they might be relying more on those superficial patterns in the data, rather than having a deeper grasp of the mathematical concepts themselves. They're good at recognizing a problem they've encountered before, but then you switch it up a little and they're lost.
So are we saying these AIs, they're basically just really, really good at mimicking what they've seen before, but they don't actually get the math?
That's exactly what these researchers are getting at. They're saying, hold on, maybe we need to rethink how we're evaluating these models. Just because they can get a high score on a fixed set of questions, it doesn't automatically mean they understand the underlying concepts.
It's like that saying, you can lead a horse to water, but
you can't make it understand fluid dynamics.
Exactly. All right, so we've established that things might not be as they appear when it comes to AI and math. They might be straight-A students on paper, but are they truly mathematical thinkers?
Let's keep digging into that. So they've memorized the steps of a dance, but they haven't really learned the music.
That's a great way to put it. And to take it even further, see if these LLMs could handle a real curveball. The researchers, they came up with another little twist. They called it GSM-NoOp.
GSM-NoOp. Okay, you're going to have to break that one down for me. What's the NoOp even stand for? So, no operation. And it's honestly kind of genius how they tested if these models are really understanding the problem or just getting hung up on random information.
Yeah.
They took those math problems and they started adding in these little details, that had absolutely nothing to do with the calculation at all.
Okay, you got to give me an example. How do you sneak useless info into a math problem?
All right, picture this. Sarah buys 5 apples, gives 2 to her friend. How many apples does Sarah have left, given that it's a sunny day?
Okay.
That sunny day bit. Totally irrelevant to the actual math.
Sneaky. Did the AIs fall for it? Did they start factoring the weather into their apple calculations or something?
Oh, you bet they did. A lot of the LLMs walked right into that trap, tried to use those irrelevant details, and it led to, well, some pretty interesting answers.
That is fascinating. So it's not just about recognizing a pattern for these AIs. It's also got to be about figuring out what's actually important to the problem, tuning out the noise.
Exactly. And that is so important because, let's face it, in the real world, problems are messy. They're not usually going to show up as a nice, neat little equation. Being able to tell what matters, what doesn't, that's key to finding the right solution.
Makes you wonder, are we expecting a little too much from these models? I mean, even we as humans, we get bogged down with too much info sometimes.
They
Think about those word problems back in school, right? All those extra details just to throw you off.
Sure, sure. But there's a difference between humans making the odd mistake and like a systematic flaw in how a model processes things. What this research is suggesting is some LLMs, they might not truly be understanding the math the way that we do. It's more like they're learning these correlations, inputs and outputs, without getting that deeper logical connection.
So less about true understanding, more like really, really good mimicry. They can follow the steps, but don't get the why behind it.
Yeah, in a way. And look, this isn't to say AI can't do any math. There's been some amazing progress with things like, theorem proving, complex calculations, all that. But what this research is saying is we got to be cautious. Just because an AI can get a high score on a test, a standardized test, doesn't automatically mean they've got this deep understanding.
It's like the difference between memorizing your multiplication tables and truly understanding what multiplication is.
Exactly. And that is a crucial distinction to make, especially as we're starting to rely on these models more and more for all kinds of things: finance, healthcare, engineering. We need AI that can not only crunch the numbers, but reason about them, adapt to new situations, explain their logic.
Which, I mean, that brings us to the big question, right? Where do we go from here? What does this mean for the future of AI and math? We've got to make sure these models aren't just spitting out numbers, but actually making sense of them. What are your thoughts on that?
So we can't just assume an AI understands math just because it can solve for X, right? Like they've got the grammar down, but not the poetry. But how do we get there? How do we build AI that truly gets it, that can appreciate those elegant equations, those clever proofs?
Well, that's the million-dollar question, isn't it? But one thing this research really highlights is we need better ways to evaluate these models. We can't just rely on those static benchmarks like GSM-AK. It's like you wouldn't judge a chef just by how well they can follow one recipe, right?
Right.
You want to see them improvise, adapt, create something new. That's what we got to do with these AI tests. We got to challenge them.
Give those AI Mad Libs a serious upgrade. Like instead of just swapping numbers and names, throw in something that really makes them think on their feet. What if, instead of basic arithmetic, we gave them some, like, algebra or calculus even? Exactly. We need to see how they handle all different areas of math. Geometry, algebra, calculus, you name it. And not just the type of problem, but the context too, right?
Yeah.
Ditch those neat little equations. Give them a real-world scenario.
Like, hand them a messy data set from a physics experiment. Or tell them to model the stock market.
Now you're talking. That kind of thing, that takes a deeper understanding. It's one thing to solve for X in a textbook. It's another to use math to design a skyscraper or predict an eclipse.
It's like a difference between solving a Sudoku and composing a symphony.
There you go. We need AI that doesn't just solve the equations, but gets what they mean. Can make predictions, come up with new solutions. Yeah, that takes a kind of intuition, a creativity that we haven't quite cracked yet.
So it's not just about teaching AI to crunch numbers. It's about cultivating that mathematical thinking, that ability to reason, to abstract, to apply those concepts in new ways.
Exactly. And that is a huge challenge. But it's also incredibly exciting because this quest to build AI that truly understands math, it's pushing the boundaries of how we understand intelligence itself. What does it even mean to understand something? How do we learn? How do we reason? These are questions people have been wrestling with for centuries.
It's like we're trying to teach AI to see the beauty of a geometric proof, the elegance of an equation. We don't just want calculators, we want collaborators, fellow explorers in the world of numbers.
Now, that is a fantastic way to put it. And who knows? In trying to teach AI to think mathematically, we might learn something new about our own cognitive abilities along the way.
It's true, and I think it's safe to say today's deep dive has shown us there's still so much to uncover when it comes to AI and math. It's a field full of surprises and really big questions. What do you think out there? What other ways could we test if AI truly gets math? What challenges could we cook up to really put their skills to the test? Something to think about as we keep exploring this amazing frontier of artificial intelligence. Until next time, stay curious. All right, so everyone's saying AI is going to be writing novels, composing these crazy symphonies, maybe even solving climate change. But can these large language models actually think? Can they really reason through a problem the way we do? That's what we're diving into today.
Yeah, and not just, adding numbers or something. We're talking about real logical reasoning, step by step, the kind of thing we thought until very recently was totally unique to humans.
Exactly. And we're looking at some really cutting-edge research here. This paper called GSM-Symbolic, Understanding the Limitations of Mathematical Reasoning in Large Language Models. They really get into it.
Oh, absolutely. At the heart of it, they use this benchmark called GSM-AK, which is a data set of grade school math problems. Think back to those word problems about trains and distances and stuff, that kind of level.
So they're testing if these LLMs can handle the abstract stuff, not just memorizing information.
Exactly. And to really push it, they didn't just stop at GSM-AK. They actually created a whole new system called GSM-Symbolic.
Okay, so unpack this GSM-Symbolic thing for me. How's it work?
So imagine you take a GSM-8K problem, one of those word problems, and you turn it into a sort of fill-in-the-blanks template. Instead of Sophie has 31 blocks, its name has object.
So you're changing the specifics, but the underlying math problem is the same.
Exactly. This way they can generate tons of different versions of the same problem. Change the names, the objects, the numbers, but the core logic is always the same. It's really clever. Lets them see if the LLMs are understanding the problem or just reacting to the way it's phrased.
And you are not going to believe this, but those tiny little changes, they make a huge difference. We're talking LLMs getting one version totally right, then bombing a slightly different version, even though the math is the same.
Yeah, it was pretty surprising. And this inconsistency is a big deal because it makes you wonder how reliable our evaluations of these LLMs have really been.
So does this mean that LLMs aren't really reasoning? Are they just picking up on patterns?
That is the million-dollar question, right? And the researchers, well, they've got some pretty compelling evidence that points in that direction. This inconsistency, it really seems to suggest that they're relying more on pattern matching than actual understanding.
So if they're just picking up on patterns, wouldn't changing a name, throw them off even more than changing a number?
You would think, right. But actually, they found the opposite. LLMs were surprisingly robust to those sorts of changes.
So swapping Sophie for John didn't matter.
Not as much as you'd expect, no. But here's the thing, and this is where it gets really weird. Even though it didn't totally throw them off, changing the names still led to these weird variations in performance.
So even these little tiny changes that shouldn't matter, they can still mess up the LLMs.
Yeah, exactly. It's like they're focusing on details that don't matter, at least from a purely mathematical point of view. And that actually brings us to another fascinating thing they looked at, the impact of complexity.
Okay, so are we talking giving them calculus now?
No, nothing like that. The math was still at a grade school level, but they played around with the structure of the problems. So they created versions with more clauses, to make them longer, more intricate, like adding extra turns to a maze.
So more twists and turns means more chances for the LLMs to get lost?
Exactly. They made 3 versions. GSM-M1, which had 1 fewer clause, GSM-P1, which had an added clause, and then GSM-P2 with 2 added clauses. And the results were really clear. The longer and more complex the problem, the worse the LLMs did.
So they're not ready to do my taxes anytime soon?
Probably not. But it does point to something really crucial here. Even if LLMs are great at mimicking human language, they seem to struggle with that step-by-step logical reasoning that we need for those more complex problems. But it gets even more interesting. Remember how we were talking about those little irrelevant details tripping them up? Well, they took that to a whole new level with something they called the NoOp test.
NoOp, no operation needed. Are they messing with these things on purpose now?
Kind of. They started putting in these little bits of information that sounded important, but didn't actually affect the answer to the problem.
Okay, I need an example. I got to see this.
Right, so picture this. A baker makes 12 cupcakes.
Mm-hmm.
Then he makes 17 more. He decides to try a new frosting recipe, but it doesn't turn out quite right. How many cupcakes does he have in total?
Okay, so that whole frosting thing, totally irrelevant.
Yeah.
It's there to throw them off.
Exactly. And you know what? The results were kind of shocking. Even some of the most advanced LLMs, their performance dropped, sometimes by over 65% even.
Wow, over 65%. That's a huge difference. They got so caught up in the story part, they forgot what they were even supposed to be doing.
It really shows you there's this fundamental challenge here. They're not really understanding how the numbers relate to each other, the logic of it. It's more like they're trying to find a pattern, something they've seen before, even if it means getting hung up on these relevant details.
Okay, so where does this leave us? Should we be worried? Are LLMs all hype, no substance?
Well, I wouldn't go that far. It's important to remember these models, they're still pretty amazing, right? The way they process language, how they can sound almost human, is groundbreaking. But this research, it's a good reality check.
Yeah, it's like we've been so busy being impressed they can stack blocks, we didn't stop to ask if they actually understand why the tower stands up.
Exactly. Mimicry isn't understanding. And when you get to something like math, where logic and abstract thought are so important, that's where that difference becomes really obvious.
So what do we do? How do we actually make these LLMs, smarter, more discerning?
And that's the really exciting part here. This GSM symbolic thing, it's not about writing LLMs off. It's about giving us better tools so we can really figure out what they're good at and where they struggle. When we understand how they mess up, then we can come up with better ways to train them, new approaches entirely.
So it's less about saying LLMs are bad at math and more about, okay, how do we teach them?
Exactly.
Yeah.
This research is like a call to action for anyone working on AI. We need more sophisticated ways to evaluate these models to train them if we want them to live up to their potential.
It really does feel like the beginning of something huge, We've opened this door to AI, but now we're seeing how much more there is to learn.
We're just scratching the surface. And every new discovery, every new benchmark like this GSM symbolic, it brings us a little closer to understanding what these models can really do.
Who knows, maybe one day they'll be the ones teaching us about math. Well, that's all the time we have for today's deep dive. We hope you've enjoyed this look at the world of LLMs and their mathematical adventures. Until next time.
Hey, everyone. So we're always hearing about AI becoming these like math whizzes, right?
Right.
Well, get ready for a deep dive into some research that's really challenging that idea.
Yeah, it's a paper called
What's it called?
GSM-Symbolic, Understanding the Limitations of Mathematical Reasoning in Large Language Models.
Kind of a mouthful.
It is a mouthful.
Hey, don't worry. We're going to unpack it.
Yeah, we are. And just to be clear, this isn't about some AI uprising or anything. This is about really understanding how these models kind of think about math, where they excel, and more importantly, where they stumble a bit.
Yeah, separating like the hype from the reality.
Exactly. So for those of us who haven't spent our days, knee-deep in algorithms, let's start with the basics. So you've probably seen headlines about large language models or LLMs solving complex math problems. But how do we even begin to test an AI's math skills? Yeah, so imagine a standardized math test, but, designed specifically for AI. That's essentially what GSM-8K is.
Okay.
And it's been kind of a popular benchmark for assessing how well these models can actually reason through, mathematical concepts.
So it's like the SATs for AI?
Kind of, yeah, in a way.
Oh, really?
But instead of cramming vocabulary and sweating over geometry proofs, these AI models are fed massive amounts of data and then tested on their ability to apply that knowledge to solve the problems.
Okay, so that makes sense. But now we've got this new research paper that's introducing something called GSM-Symbolic.
Yeah.
What exactly is that, and how does it kind of build upon GSM-8K?
So think of GSM-Symbolic as a stress test for these LLMs.
Okay.
It takes those same GSM-8K math problems but creates tons of variations.
Right.
Imagine taking a math problem and just slightly changing the names used, the numbers, or adding a few totally irrelevant details.
So instead of asking, if John has 3 apples...
It's like if Sarah has 5 oranges.
Exactly.
Okay.
And the goal is to see if the LLM can still arrive at the correct answer. Even with these seemingly minor tweaks, it helps us understand if it's truly grasping those underlying mathematical concepts or just getting by, on memorization and pattern recognition.
So it's the difference between understanding the concept of multiplication.
Exactly.
Versus just memorizing your times tables, right?
Yeah. And what the researchers found when they put these LLMs to the test with GSM-Symbolic is, well, it's pretty revealing.
Yeah, and that's where it's really interesting. So what did they find? Were these AIs as sharp with their math skills as everyone's been saying?
Well, not exactly. One of the first, red flags the researchers discovered was that these LLMs could be incredibly inconsistent in their performance.
Really?
They might solve one problem perfectly and then totally stumble on a slightly varied version, even if the underlying math was essentially the same.
Wait, so they're acing a problem 1 minute. Yeah.
And then blanking on a nearly identical one, the next. That's kind of strange, isn't it?
It is. It suggests that these LLMs might be relying more on maybe like superficial patterns
Okay.
in the data they've been trained on, rather than like genuinely understanding those mathematical principles that are really at play.
So it's like they're mimicking what they've seen before
Yeah.
without actually like truly grasping the logic.
That's the question this research is raising, right?
Right.
It challenges this whole notion that these models have like suddenly become these mathematical geniuses.
So they're not ready to be our robot math tutors just yet.
Not quite.
Okay.
But it gets even more interesting when we look at how these LMs respond to very specific types of variations in the problems.
You mean like when they change like the names versus changing the numbers in the GSM-Symbolic problems?
Exactly.
Tell me more. Tell me more.
So what's fascinating is that the researchers found that LLMs were much more sensitive to changes in the numbers within the problems than they were to changes in like the names.
Hold on. So if I'm understanding you correctly, NLM might like stumble more if we change a like 3 to a 5 in a word problem.
Right.
But it's less phased if we swap out like Alice for Bob.
Yeah.
Why would that be?
That's the million-dollar question, isn't it? It suggests that LLMs might be like fixated on the specific numerical values that they encounter rather than those underlying relationships between those numbers. You know, think about how you like as a human would approach a math problem. You'd likely focus on the relationships between the quantities involved, not the specific digits themselves.
Right.
Like if you have 3 apples and you get 2 more, you understand that's the same as having 5 apples.
Right.
Regardless of whether we're talking about apples or oranges or, you know, something else entirely.
That's true. Yeah. For me, it's more about the concept, not the specifics.
Yeah.
But it sounds like these LLMs might be like getting a little too hung up on those specifics.
That's what this research suggests, yeah. And to make things even more interesting, the researchers found that this sensitivity to numerical changes, it actually became even more pronounced as the math problems get longer and more complex.
So it's like they have like a limited attention span when it comes to numbers.
Yeah.
Like how if a recipe has too many steps, I can't.
Yeah.
Yeah.
It's an interesting analogy.
Right.
But yeah, in the context of these LLMs, it raises some, I think, important questions about their capacity for handling like true complexity in mathematical reasoning.
It makes you wonder, like, are they really grasping those deeper relationships?
Yeah.
Or are they just like really good at pattern recognition? You know?
Exactly. And to really put these LLMs' reasoning abilities to the test, the researchers threw in another curveball called NoOp statements.
NoOp statements. What are those?
So imagine adding like a completely irrelevant detail to a math problem.
Okay.
Something that doesn't actually change the underlying calculation, but might distract you.
Yeah.
If you're not paying like super close attention.
Okay, I'm with you. So give me an example. Like what kind of irrelevant detail are we talking about?
So in one of the problems, the researchers added a line mentioning that some of the kiwis were smaller than average.
Okay.
And this detail had like absolutely no bearing on the total number of kiwis.
Right.
Which was what the problem was actually asking about.
So it's like saying Sarah has 5 oranges and her favorite color is blue.
Exactly.
Okay.
Right.
It's true, but it doesn't change anything about the oranges.
Exactly. And you, as a human, would likely recognize that and simply, you know, ignore that irrelevant information.
Yeah, just kind of filter it out.
Yeah, but surprisingly, the LLMs, they often stumbled on these NoOp statements. Like they tried to incorporate that extraneous information into their calculations, even though it was totally unnecessary.
Wow. So they were so focused on like the size of the kiwis.
Yeah.
That they just like totally missed the bigger picture.
It's kind of, mind-blowing when you think about it.
That's kind of mind-blowing and a little worrying if you really if you extrapolate that out.
It does. It makes you question, you know, how well these LLMs are truly understanding these problems versus, you know, simply reacting to like these surface level patterns in the data.
So where does that leave us then? What's the takeaway here for like, you know, for me or like anyone who's been following the advancements in AI and wondering like, okay, are robots about to take over like math class?
Well, I think the most important takeaway here is that we need to kind of approach claims about, you know, AI's mathematical prowess with a healthy dose of skepticism, right?
Okay.
But this research really highlights some of the limitations of LLMs, at least in their current state. They're not, they're not magical mathematical oracles or anything.
So they're not going to be like publishing groundbreaking math papers anytime soon. Is that what you're saying?
Probably not, no. but in all seriousness, this research reminds us that true mathematical reasoning, it's a very complex process, right? It involves more than just, pattern recognition.
Right.
It requires, understanding. It requires flexibility, the ability to kind of abstract and generalize.
Qualities that, we humans, for all of our flaws,
right,
seem to possess in a way that AI just hasn't quite mastered yet.
Exactly. Yeah. And while, LLMs have made remarkable progress in many areas, this research really suggests that we still have, a long way to go before they can truly replicate those nuances of human-like reasoning, particularly in the realm of mathematics.
Okay, so no robot math tutors just yet.
Not yet, no.
But it does raise these big questions, though, right?
Yeah.
Like if these LLMs are struggling with these relatively basic, math distractions,
right?
What does that mean for more complex reasoning tasks?
Right. That's an excellent question.
Right.
That's a perfect segue almost into a larger discussion.
Into a larger discussion about the implications of these findings. If these LLMs are tripping up on these, seemingly simple problems.
Yeah.
What does that mean when you're talking about the really intricate stuff?
Exactly. So we're talking about things like developing new algorithms or proving complex theorems,
right,
or making high stakes decisions in fields like, finance or medicine areas where even a tiny little error in reasoning can have massive consequences.
So this isn't just about AI, struggling with word problems. It's really about their limitations in handling this kind of abstract, high-level reasoning that really underpins so much of what we consider intelligent behavior.
Exactly. Yeah. And it highlights this importance of not overestimating the capabilities of these LLMs.
Yeah.
Based on, how they perform on these narrowly defined tasks.
Right.
Just because an AI can, outperform a human in a controlled setting, I don't know, game of chess or Go or something, doesn't mean that it suddenly possesses, the same, depth of understanding as a human expert.
So, assuming someone who's, really good at memorizing, trivia facts is automatically, a genius or something, they might be able to recall a lot of information.
Yeah.
But it doesn't necessarily mean, deep understanding or critical thinking.
Exactly. Yeah, that's a great analogy. And it kind of brings us, I think, to a really crucial point here. While this research might seem on the surface a bit of a setback for AI development, it's actually incredibly valuable because by identifying these limitations, we can actually start to develop more robust and reliable AI systems in the future.
So this research is a good thing. It's giving us a more realistic picture of where we are and helping to guide future research.
Exactly. Yeah. It's like a reality check. It can help us direct our efforts toward, developing AI systems that are not just powerful, but also trustworthy and reliable.
Right. So it's about moving beyond just simple benchmarks.
Exactly.
And really focusing on building AI that can truly reason. And understand the world in all of its, complexity.
100%. Yeah.
So while we might still be a ways off from having, AI mathematicians, revolutionizing the field.
Sure.
This research is a really crucial step in the right direction.
Yeah.
It's helping us understand not just what AI can do, but how it thinks. And where its limitations, currently lie.
And for the listener who's, really fascinated by this world of AI and its potential,
Right.
This research is a really, I think, powerful reminder that we're still in those, kind of early stages of a very long journey.
Yeah.
There's still so much to discover, there's so much to explore, and it's important to, I think, approach these advancements with a balance of excitement,
Right.
but also that healthy skepticism as well.
Yeah. Don't believe every headline you read.
Exactly.
Yeah.
Dig a little deeper, ask questions,
I
stay
agree.
curious. This future of AI, I think it's just, it's full of possibilities.
Yeah.
Understanding like the limitations of today's technology is really key to, unlocking the full potential of tomorrow's breakthroughs.
Well said. Well said. It's been really, really insightful deep dive into, the world of LLMs and mathematical reasoning. A huge thank you to you for joining us.
Of course.
And sharing your expertise. And to you out there listening, thank you for joining us on this journey of discovery. We hope you found this deep dive as thought-provoking as we did. Until next time, keep those minds curious.